In this video, we'll be exploring what reaction rates are and the factors that affect them. Starting off, let's define what a reaction rate is. Remember that in a chemical reaction, we are starting with a set amount of reactants and we're forming some products. A reaction rate describes the change in concentration for a reactant or product over time. And they're typically going to be expressed in molarity per second, which just means the change in our molarity or our concentration over time. And so then this is just another way we could write it. Remember that this triangle delta means change, so this is change in concentration of A over our change in time. As shown by this chart, as a chemical reaction progresses, we are consuming reactant to form product. So the concentration of our reactant, our purple line, is decreasing over time. And the concentration of our product, our green line, is increasing over time. Thus, in the future, when we're going to be writing out a reaction rate for a species, we're going to use a negative for our reactants. Because remember, their concentration is the one that's decreasing. And then for our products, we'll be using a positive sign because they're going to be increasing in concentration. Another thing I want to point out about this graph, and something you definitely have to know, is that as our reaction proceeds, so as our time is increasing, the rate at which our reaction is proceeding decreases. That just means the rate at which we're consuming reactant and the rate at which we're forming product is going to decrease. Make sure you know that. As we've seen by now, we're commonly going to be measuring our reaction rates by looking at the change in concentration of a species in a chemical reaction. However, there are some other ways in which we can measure reaction rates. We can also look at the change in mass for our species, or even the change in pressure, or the change in color for our reaction. While you're only going to be expected to do calculations with the change in concentration, it's important to know that there are other ways of measuring a reaction rate. Next, let's look at the stoichiometric relationships for reaction rates. Let's say that we've got this chemical equation here, where our reactant A is forming product B. Because both of our species have a coefficient of 1, then the negative change in the concentration of A is going to equal the exact same as the positive change in the concentration of B. Alright, and so another way of saying this is the rate at which the concentration of A is decreasing is equal to the rate of the concentration of B forming. Now, imagine that we've got a chemical equation where 2 moles of reactant A are forming 1 mole of product B. So this time, 1/2 the negative change in A will equal the positive change in B. And remember, that's just because we've got this coefficient of 2 out in front of here. Sorry if that was confusing, but this right here is pretty much the way you should be thinking about it. And just to unpack this, we have our coefficient of a lowercase letter, and then our actual species uppercase letter. You take your coefficient and you put it in the denominator of a 1 fraction, and then you just see the concentration right here. And so that's how you can make sure your stoichiometric relationships are always correct when solving these reaction rates problems. Make sure to always keep them in mind because they are going to be quite important. Back to our reaction rates, there are 2 different types of reaction rates we can find: an average rate and an instantaneous rate. The average rate is going to be the change in concentration over a set period of time. For instance, it could be talking about the change in concentration for our reactants from 10 to 40 seconds. In which case, we would have 2 different points, our starting point and our ending point, and we would just find the slope connecting these. The instantaneous rate is the change in concentration at a specific time, a specific instance in time. So imagine again that we have our graph. The instantaneous time could be asking, for instance, what is the change in concentration at exactly time equals 10 seconds? For those of you that have taken calculus, the instantaneous rate is the derivative of the concentration line at that time. So it's going to be the tangent line to the concentration time curve at this moment. And so if we were to draw that in, the slope of this tangent line is going to be our instantaneous rate. If you haven't taken calculus yet, just think of this as the change in concentration for a certain moment. For instance, at this 10 seconds, what is the current slope for our change in concentration? You won't be expected to do any calculus derivatives in AP Chemistry, so don't worry if you haven't taken calculus yet. But so that's the difference between our average and our instantaneous rates. When it comes to our instantaneous rates, we can write something called a rate law. And a rate law is pretty much what the first half of Unit 5 is going to be about. So make sure you're paying attention right now. What a rate law does is it shows how the concentration of our reactants affects the speed at which our chemical reaction progresses. Again, if we're looking at this concentration time graph, depending at which time we start at, we're going to be drawing different tangent lines to our reactant curve. And you should most definitely be able to see that the slope of this line over here is much bigger than the slope of this line over here. That's a much smaller slope. And so what a rate law does, it's an equation which quantitatively links the concentration of our reactants to the speed at which our chemical reaction is going to take place. And so the equation I've written here is the basic blueprint for our rate law. The rate at which our reaction progresses is equal to K, that is our rate constant, times the concentration of our reactants, A and B. Remember, we're only doing reactants in a rate law, raised to the M and N respectively. And M and N are known as our reactant orders. And so essentially what you do is we plug in our rate constant, we plug in our concentration, and then we just solve for the rate, which is going to be a numerical value, giving us the speed at which the concentration of our reactants are changing. We'll be going over how to write rate laws and compute them in future videos. So for now, you only need to know this basic blueprint. And the very last thing we have to go over in this video is the factors affecting our reaction rates. Remember that for a chemical reaction to form products, our reactants must collide with sufficient force and correct orientation. Only when this happens correctly can reactants actually rearrange to form products. Thus, one way to increase the rate of our reaction is by increasing the surface area of our reactants. This will increase the frequency of our collisions, thus increasing the percent of successful collisions. Additionally, by increasing the concentration of our reactants, again, we're going to be increasing the frequency of our collisions, thus increasing the amount of successful collisions. The same is true for increasing the pressure or temperature of our reaction. Again, we're just increasing our collisions, which should theoretically increase the percent of successful collisions. And then the last thing we can do is introduce a catalyst into our reaction. This is going to lower the activation energy of our reaction, thus speeding up. Catalysts will be covered in a future video, so don't worry about that right now. The only thing you need to have a strong understanding of right now is that performing these actions will increase the rate of our reaction. And with that being said, that's all you have to know for reaction rates in AP Chemistry. If any of this was unclear, I recommend rewatching parts of the video. If it's still not making sense, take a break and come back after. Thank you for watching.